Hello guys, and welcome to another calculus video. In this video we're going to be finding the exact real value of this integral right here, the indefinite integral of 1 over x to the 5th plus 1 dx. Now I don't do a lot of indefinite integrals on my channel recently, but I thought this was a pretty interesting one because it definitely applies to a lot of other the skills in this for this problem definitely apply to a lot of other rational integrals, so I figured I'd give it a little bit of a shot, especially because we use some very interesting methods here. So first, we're going to do some really quick lemmas that will help us when integrating with complex numbers. And this concerns a complex number z equals a plus bi, and its conjugate z bar, which is a minus bi. So if we have 1 half I over x minus z minus I over x minus z bar dx all integrated, we are going to do some algebraic manipulation with the natural logarithms here, and actually we will end up with a form of the arctangent function. In fact, it'll be negative inverse tangent of x minus a over b plus c. And that's going to come up a lot. We're going to mostly be dealing with conjugates. And then when there's no imaginary numbers and these two are being added together, we can just combine the natural logarithms to get ln x minus a squared plus b squared plus c. So let's go ahead and jump right into the problem. We have x to the 5th plus 1 equals 0. We want to find the zeros because that way we can factor the bottom and do partial fractions. So we set x to the 5th equal to negative 1. And negative 1 is, of course, e to the pi I plus 2 pi I n. And we find that x equals e to the pi I times 2n plus 1 over 5. Now n is going to be 0, 1, 2, 3, or 4. I've plotted out the 5 zeros right here on a complex plane on the circle modulus of z equals 1. So notice we have these two conjugates right here, these two conjugates right here, and then x equals negative 1 right here. So we're going to be sort of combining the terms with the conjugates in order to make our integration easier. So, notice I've used some product notation to denote the factorization that we've done in the bottom here. And then we can actually write this as the sum from n equals 0 to 4 of an over x minus e to the pi I times 2n plus 1 over 5 dx. This is just after doing partial fractions. We still need to find the value of an. So in order to do this, we're going to do the cover-up method. Now the cover-up method basically says, in order to find the value of these coefficients an, we can simply plug in the value of the 0. So for example, for the term when n equals 1, we can just plug in the value e to the pi I times 2n plus 1 over 5, where n equals 1. We can plug that in to the rest of the rational function and just ignore that one term where it's going to be 0, just cancel that out. And that will allow us to find the coefficient. And in this case, actually plugging it in into all of those terms is going to be very difficult. So that's actually the same thing as taking the limit as z goes to the z goes to e to the pi I 2n plus 1 over 5 of z minus zn, where this is zn over z to the 5th plus 1. And the reason we're doing this right here is because this z minus zn will cancel with the z minus zn in the bottom when we evaluate the limit and give us what we want. However, there's also another way to do this, and that's just using the Hospital's rule, which is super easy. This gives us 1 over 5 times zn to the 4th, or e to the pi I times 2n plus 1 over 5 e to the pi I times 2n plus 1. This is just negative 1, so we get negative 1 over 5 zn. So now we can go ahead and integrate, and we're going to get negative 1/5 sum from n equals 0 to 4 of zn natural log of x minus zn plus c. So we're going to analyze the conjugates together. So we're going to first look at z0 and z4, then we're going to look at z1 and z3, and then we're going to do, we'll do z2 first. So see, z2 is negative 1, so our integral term is just going to be 1 over 5 times natural log of x plus 1. And so that's all we need to do for that one. But for z0 and z4, we're going to combine these together. So I've written them out in their trigonometric forms here. So this is the actual sum of the integrals of both of them. We have negative 1/5 cosine pi over 5 plus I sine pi over 5 times natural log x minus z0 plus cosine pi over 5 minus I sine pi over 5 natural log of x minus z over 4. And then all we have to do here is simply combine the cosine terms and the I sine terms, and they actually apply exactly to those formulas that I showed at the top. So we can just go ahead and apply that directly. And this is what we get right here. Next, notice that this isn't fully simplified since we don't have the values of cosine pi over 5 yet, or sine pi over 5, but we'll deal with that later. Next, let's look at z equals 1 and z1 and z3. And again, it's going to be the same exact thing. We're going to take these cosines and these sines and we're going to combine them. We end up with one natural log term and one inverse tangent term. So analyzing complex conjugates is so important whenever we're integrating rational functions because it allows us to take these very, very complex values and figure out how to combine them in the right way to get real functions out of it. So now the hard part, we want to find the values of sine pi over 5, cosine 3 pi over 5, and all those different things. We can use these identities right here. Importantly, if we let theta equals pi over 5, then we know sine of 3 theta equals sine of 2 theta, because sine of pi minus theta equals sine theta. So after doing some algebra, we find that cosine theta is 1 plus root 5 over 3, or over 4, sorry, and sine theta is 1/4 times root 10 minus 2 root 5. And then using identities for 3 theta, we can pretty quickly find that sine 3 theta and cosine 3 theta are these values right here. And then we can go ahead and plug the values into our expression from earlier. I was really too lazy to write all of this out, but here's the final answer right here. And that's it. Oh, something I just noticed that I did. Oh, never mind. Sorry. Yeah, this is right. Right here. And that should be it. Yeah. So I hope you guys enjoyed the video. I hope you learned something about these different methods that we can use when integrating rational functions. And yeah, thank you for watching, and I'll see you next time.